This is 2019 paper 1 question 7. So we have this thing called the Cantor set where we have a line from 0 to 1 and then we're removing the middle third of this segment. And then we have 2 segments, and then we remove the middle third of those 2 segments, and then we have now 4 segments, and we keep removing the middle third of all the segments. So we have to complete a table showing the length removed at each step. So in the first step, we just remove a third, because we remove a third of this line. In the second step, we remove 2/9, because a third of this line, for example, well, this line has a length of a third, so a third of this third is going to be a 9th, and then we're doing that twice, right? So we remove a 9th here, and we remove a 9th here, so we get 2/9. So we can continue. So here, each length is a 9th. So what's a third of a 9th? Well, 1/9 times 1/3 is 1/27. And then we're going to remove that 4 times. So we have 1/27, 1/27, 1/27, 1/27, and we're removing all of those. So what we'll get is we're doing that 4 times, so we'll have 4/27. So we'll have 4/27. And then at this point, you might see a pattern. So on the top, we have the powers of 2, and on the bottom, we have the powers of 3. So you can just you can reason on that if you want, but the next one is going to be 8/81. And the reason for that is because here now we have 8 segments, and we're going to be removing 1/81st from each segment. And then we're going to have 16/243, because when you multiply 81 by 3, you get 243. Then for part 2, we have to find the total length of all the line segments removed from the initial segment. So this is all the line segments removed, and we have to add these all up pretty much, because we need to get the total length of the removed amount. So what we might notice is to go from one to the next, it's a geometric sequence, with the first term is a third, and each time we're multiplying by 2/3, right? Because on top we're multiplying by 2, and on the bottom we're multiplying by 3. So we can use this formula for the sum of the terms in a geometric sequence, and what we'll get is that Sn will be equal to a third times 1 minus 2/3 to the power of n, all divided by 1 minus 2/3. And this works out quite nicely, because we'll have a third times 1 minus 2/3 to the power of n, all divided by, and 1 minus 2/3 gives you 1/3. So we're multiplying and dividing by a third, so they will cancel out, and we'll get 1 minus 2/3 to the power of n. And then we're told to find the total length removed after an infinite number of steps in the process. So it should make sense that, I suppose, as we remove more and more lengths, the total length that we're left with is getting smaller. And after an infinite number of steps, we basically have no length left, because we keep taking out length. And that's supported by the formula. As n gets bigger and bigger, this term gets closer to 0. So then the amount that we've removed, which is Sn, gets closer and closer to 1. So you can use the infinite sum of a geometric sequence formula in the tables book, or you can just do it with limits, which I think is just a little more intuitive and faster. So as n goes to infinity, 1 minus 2/3 to the power of n, well, because the 2/3 is less than 1, that means that when you keep multiplying this, it's going to keep getting smaller, so it'll eventually go to 0 as n goes to infinity, so the answer is 1, which should make sense, because as time goes on, we're going to keep removing more and more, so as n goes to infinity, the amount that we've removed gets closer to 1, which is the total amount. For part B then, we have to complete this table. So first of all, the point A, well, we can see this is 0/3, this is 1/3, and we're moving the middle third, right? So if we split this up into thirds, this part's going to be 2/3. We're moving that middle part, so A is clearly going to be 2/3. And we can use a similar thing to figure out what B is. So this is a 9th. So again, if we're splitting this up into thirds, well, we're splitting now 0 to a third into thirds. So if we're splitting into thirds, this is going to be 1/9, this is going to be 2/9, and this is 3/9, which is the same as 1/3. So clearly B is 2/9. Go to C, we have a similar thing going on. So again, we're starting here at 2/3. Okay, as you can see from down there, we're ending at 1, and we need to split this up into thirds. So 2/3 is 6/9, so this will be 7/9, this will be 8/9, and then this here is 9/9, which is the same as 1. So clearly C is 7/9, and D kind of comes for free then, it's 8/9. Then if we have a look at E, okay, so it's starting to get a little more complicated, but B here is 2/9, so I actually might just bring this out to the side. So I've just taken this segment here, right? So B is 2/9, and then it goes up to a third, which I'm just writing as 3/9 to make things clearer. And if we split that up into 3 segments, well, this segment, so I guess if we split these up into thirds, we're gonna be talking about 27ths, because a third of a 9th is 27. So if we think about 27ths, well, I can multiply the top and bottom here by 3. So 2/9 is gonna be the same as, it'll be 6/27ths, and then 3/9 will be the same as 9/27ths. So if we're splitting this up into thirds, well, then this is going to be 7/27ths, and it's going to be 8/27ths. And you can see we've split this up into equal parts, so into thirds, and we can see E or E is what we're looking for. Yep. So E is going to be 7/27 because this is B here. So it goes B, E, and then we're going to be removing this middle third. And then we have these ones. So E clearly then is going to be 8/27. And then if we look for F, sorry, B is, or E is 7/27. It's this, it's on the left. Here is 7/27. On the left, on the right is the 8/27. So sorry, that should be 7/27. And then for F, we just got a similar thing going on. So if we look at D going to 1, so if we have D here, and then we have 1, and then we're going to connect those together. So D, what is D? Well, we can see from our diagram that D here is 8/9, right? So D is 8/9, but again, we'd like to work in terms of 27ths. So instead of writing 8/9, I'm just going to write it as a 27th. I'll just move them down a little bit. So D is 8/9, as I've said. So if you multiply top and bottom by 3, 8/9 is the same as 24/27. Of course, this is 27/27. So if we split this up into 3 equal parts, we'll have 25 out of 27, and we'll have 26 out of 27. And then we're removing this part here in the middle. So this is equivalent to this part here, removed in the middle. So you can see F is the bit on the left, so F is going to be 25/27. So a bit of a tricky question, but hopefully that made sense. Then we're told to give a reason why this is a point in the Cantor set. So let's just have a look at what this is actually, I suppose, what is it on the diagram? So we look on the diagram, if we go to a third, that's going to be here, so that's a point. Then minus a 9th will bring us to here, which is the same as B, so that's clearly a point. Add a 27th, which is going to be a third along here, and that's going to give us E. So I suppose the first thing we could say is that a third minus a 9th plus 1/27th is a point in the set. And then we just need to deal with that last 1/81st. So what might help is if we just do a sketch. So here we have E, and we said what E was up above. E was 7/27. So here we're going to have 7 out of 27. And then on the left here, that's B. So that's going to be 2/9. But again, we'll just write it in terms of 27ths. So we can write that as 6/27. So 6/27. And this is kind of our little line segment here. And we need to split this up into thirds, right? So we split this up into thirds. So split it up into thirds. So if we're splitting it into thirds, it helps think of these as 81sts. So instead of writing 6/27, you can write that as 18/81sts. And same over here, multiply by 3. So it's 21/81sts. So then we're removing this part in the middle. So now the endpoints are here. So this is going to be 19 out of 81. This is going to be 20 out of 81. And then that makes sense because this is 21 out of 81. So we ended up here at a third minus a 9th plus 1/27th, and we said that was E. So E is 7/27 or 21/81. And then if we go to the left by 1/81, you can see that that brings us to another point. So that's the same as subtracting 1/81. So you can say that this is a point, and then I suppose you could say when you go back by 1/81, you reach a new endpoint for that reason. So if that doesn't make sense to you, you can kind of do it any way you want. So in the marking scheme, it suffices to say that it was just an endpoint or a start point. Then they did out the thing that I just did, where they're showing which point it actually is. Or you could literally just say that 7/27 minus 1/81 is a point in the Cantor set. So yeah, basically it would the way that you should approach it is just by kind of going through all of them and then checking, is this actually a point in the Cantor set? Then we're told that the limit of this series is a point in the Cantor set. So if we look for the geometric sum, that's a times 1 minus r to the power of n, all divided by 1 minus r. And of course, as n goes to infinity, well then r to the power of n is going to go to 0. So the sum at infinity will be equal to a times 1 divided by 1 minus r, because as r goes to 0. So it's just going to be a over 1 minus r. And that's in the tables book. You don't have to derive it, but that's just showing where it comes from. Here, a is a third because we're starting at a third. And each time we're multiplying by minus a third because the signs are alternating. So r is minus a third. So the sum to infinity will be equal to a third divided by 1 minus a third. So that's equal to a third divided by, that'll be 1 plus a third, which is 4/3. Multiply the top and bottom by 3, and you'll get 1 over 4 as your answer.